Welcome to HB Tuner's GM Gen 5 training part 34. In this training module, we're going to be taking a look at our closed loop operation once again, and this time we're going to be exploring using the proportional and integral gains to drive the response from our closed loop behavior. We have a lot to discuss here. Let's jump in so we can check this out.
Okay, so let's get started. We're going to be taking a look at our closed loop O2 advanced parameters here. Once again, this tutorial we're going to be focusing on our proportional and integral gains and how it's going to factor into a response from our closed loop. So let's jump in here and let's talk about where we can find our closed loop, proportional and integral aspects. We're going to break down what they represent, what they mean, and then we're going to take a look at log data so we can see the cause and effect by changing them. Now I have some general suggestions when we're installing long tube headers of what the values should be altered to, but ultimately it's going to depend on how your combination of parts is going to react. You may or may not find that the suggestions I give are going to work for you, but they're just kind of general guidelines doing a bunch of Gen 5s. This will be a good starting point from what we cover here in the tutorial. Let's jump in here and take a look. I have a 2018 Yukon Denali file open. That's our test vehicle for our training course. Now the file, as we're going to be taking a look at it, is going to be stock right now in terms of all of the closed loop functionality in the programming, specifically looking at the proportional and integral aspects for the closed loop control. We're going to talk about what I changed and then look at the data logs so we can see and get an idea of before and after type of effect, so you'll get a good idea of what to expect when you're changing things on your vehicle. Ultimately, you're going to have to data log and take a look at what the data shows you. That'll show you very quickly of what changes you might potentially need to make. So, very first thing here, let's jump into our engine tab. We're going to go into general here in our tab and then move across here into fuel. And then under fuel, we're going to jump here into oxygen sensors, where we were looking at in the previous tutorial. Now, we established in the last tutorial looking at our different mode versus airflow thresholds. So we know we have a certain amount of airflow coming into the engine. We're registering that with our mass airflow sensor reading in grams per second. That's going to be the gray values up top in our table here. The actual values in the table is going to establish what airflow mode we're actually operating in. We know when we're talking about our switching voltages that put us to different portions of the table. So at idle, for example, we were more along the lines of 0 to 8 or even 0 to 16. And then part throttle cruising, we were usually 24 and higher here, depending on exact amount of airflow coming in, the throttle angle, where we're at, where we're driving. But we're going to find that we could distinguish which specific zone we might want to make changes into based on the log data and based on looking at how much airflow is coming in from the mass airflow sensor. So we've established what the airflow modes mean. Some of that's going to carry forward into the concept that's going to carry forward into looking in this tutorial at our proportional and integral gain factors down here below. So let's move from our area here, since we established that, again, understand that principle there. Let's move down to our lower portion, talking about proportional and integral. This is known as PI. If we're talking about proportional integral derivative control, that's closed loop functionality that drives the behavior in closed loop. So in general terms, talking about closed loop behavior, it doesn't matter if we're talking about looking at closed loop fuel control, or we're talking about closed loop drive-by-wire control, or any kind of closed loop control. Closed loop control is going to be having a target that we want to reach. And we're going to have sensors to measure what the actual results are happening in real time. And we compare that to the target. And what we're going to find is we can measure what's known as an error, or the difference between what we're measuring in real time and the target. Now, in general terms, that error is fed into the closed loop model, and we use the proportional and integral, and there's also another factor called derivative, which is omitted here from the O2 programming because we don't need it in order to drive the behavior of our closed loop, specifically related to fueling. But we'll find is the proportional integral derivative gains are going to be driving how the behavior of that closed loop functionality is going to perform. So meaning, if we want to reach the target, but our actual measured amount is off from the target, based on how we program the proportional integral derivative values, that'll drive it to the target and keep it at the target when we're running that specific task. So proportional integral derivative control is used in many different industries. If we're talking about pneumatic industries for machinery, proportional integral derivative control is going to be found in there.
Thanks for checking out our teaser clip. If you want to see the rest of this video and more than 500 hours of current EFI training we have to offer, make sure you click right here. If you want to go and check out more teaser clips from this training course, click here, and you don't want to miss any of the videos we're going to be releasing on this channel, so make sure you subscribe and click here. Thanks for watching, and I'll see you guys later.